Hi everyone, I'm Toan Nguyen. Today I'm gonna present our papers at WSCB 2024 titled Domain Generalization via Risk Distribution Matching. The outline of the talk will be considered of 4 parts: problem setup, methodology, experiments, and conclusions. So I'm starting off with the problem setup of domain generalization. So we are given data from m different domains, D1 to DMs, where DEs contains the corpus of images and label for domain E's. So our goal is to train a classifier F on D so that F can perform well on unseen domains at test times. For example, in training data, we may have giraffe images coming from art paintings coming from the wild, but as test time, the models faces the giraffes from very novel domains such as the sketch paintings. A naive solution is empirical risk minimization, ERMs. ERM try to minimize the expected risk across all training domains. However, ERMs is prone to spurious correlation on training domains because it tries to learn highly predictive features on training domains, but these features may not appear at test times in novel domains, result in very poor generalization. For example, in the images of elephants below, we have the model might learn the crash features, which is spurious features and may not appear with in the pictures of elephant in sketch paintings. Our motivation to solve the problem is that domain-invariant or semantic features generalize well across domains. So we require a training objective to capture domain invariance. To do so, we need a unique domain representative that both characterize each domain and provide some valuable insight into domain variation. For example, the pictures of elephants, we have the semantic features such as the trunks of elephants or the shape of the elephants. So our second motivation is that the rich distribution differences offer insightful cues into domain variation. So if we minimize these divergences, we can have a generalizable and invariant feature learning predictor. For example, we plot the rich distribution across domain art and photo of PICS trained by ERM below. As you can see, the two distributions are very different, and the key rationale behind our idea is that if the model learns invariant features across domains, it might have similar distributions across all trained domains. So the main advantages of rich distributions is that if we match the rich distributions, we can have a much more efficient solution, and we only focus on scalar distributions. And compared to other matching algorithms, it doesn't suffer from the cost of dimensionality, so we can have more accurate estimates of statistical properties when do matching between distributions. So now moving to methodology. So we denote TEs at the probability distribution over the risk of all samples in domain E. So our objective is to minimize the distributional variance across the rich distributions on the real number space. So our training objective will be consisted of 2 parts. The first one is the ERM training loss, and the second one is the loss to minimize the distributional variance to force all distributions of rich to be the same. So however, we have one difficulty is that the rich distribution of domain E is implicit. So we require a suitable presentation of TE. So we use kernel mean embedding to express TEs at the embeddings mu TEs within a reproducing kernel Hilbert space H using feature map phi. We use phi to map all the original samples in the original distribution TEs to the Hilbert space H, And the objective now becomes computing the distributional variance between risk distributions within H. So inspired by the early work, we redefined the variance matrix to focus specifically on the risk distributions below. So the distributional variance is now computed by the square norms of the difference between the mu T and mu T, where T denotes the probability distribution over the set of all M domains, and minimizing the distributional variance achieve our goals at matching the risk distributions across domains. So the square norms is actually the square maximum mean discrepancy (MMD) distance between distributions TE and T. It can be computed as follows by the kernel trick with the samples from the original distribution T and TA. So after computing the square norm using the MMD distance, we propose our methods rich distribution matching RDMs trained with the log function below, with the loss of EERMs and the loss of RDMs to match distribution. So, but however, optimizing the above log function requires OMs, the computation times of the MMD distance. So we propose a more effective approximate, which is matching the risk distribution of the worst case domains, denoted W's, with the combined risk distribution of all domains. This approach only requires one computation, focusing on matching the worst domains have several benefits. The first one is that it varies computationally efficient, and the worst mean risk domains is likely to diverge greatly from the others risk distributions. So in this case, using the worst case domains will be an upper bounds of the original risk distribution matching objective, and also focusing on the worst case domain increase the robustness of our methods to extremely training scenarios, which further improves generalization. Moving on to the experiments. We test our algorithms on a synthetic dataset color MNIST, where the task is to do binary classification with the color constraint, where each digit is colored either red or green, and the dataset is stimulated with the colored biases between training domains and test domains, and the goal is to train a predictor that is resistant to digit color features and focusing only on digit shapes features. So here you can see our matching RDM algorithm outperforms SOTA methods irrespective of the network configurations, and RDM even outperform the Oracle's models and converge towards optimality. So here's we plot the risk distributions of our methods and the baseline ERMs. As you can see, in our methods, the risk distribution are matched perfectly, and the test distributions is very close to the trained ones. We also test our methods on the domain best suit, where the task is to do image classification, and the matrix is the average sleep one domain out accuracy on all domains, and the model is tested on one domain while trained on the remaining domains. And on average, the proposed algorithm RDMs outperform the SOTA baseline, especially on the largest the dataset domain net. And from the experiments, we also see that matching with the worst case domains is potentially an upper bound of the distributional variance with only small gap, while being much more efficient. And also the learning curve of SOTA baseline. As you can see, the proposed matching algorithm outperform the SOTA baseline across the training trajectories. The application studies also show that increasing the batch size support better distribution matching and hence generalization. And if you focus more on matching distribution, it helps generalization. Conclusion: matching risk distribution across training domains improve generalization on unseen test domains. Thank you for listening.